Okay, hello everyone. My name is Gary. Hopefully you guys watched the first video on YouTube where I went over a couple of things about motors. So we're going to cover a couple of review questions off that to begin. And we'll be doing that for the following workshops too, so that you guys are, have an understanding of how everything kind of connects together. I am going to have I'll constantly be looking at the chat too. So if you didn't watch the first video, that's okay. Don't worry about it. I'll give you a summary basically before we start the sensor workshop, so you guys can kind of tap into what's going to happen next. Okay, so before I continue, actually, the first thing I want to go over is about tasks that we have for the E team. We have 3 of them. 1 is remote controller, 2 is power distribution, and 3 is where we're going to develop an emergency electrical or mechanical fill switch. All right, so the first thing, the remote controller is going to involve a little coding, basic level coding from like an Arduino or an Arduino Mega or Raspberry Pi. 2 is going to be a power distribution. That's the task that needs to get done by this year, no matter what. This year, I mean, as in by spring semester. And 3rd is going to be the electrical mechanical fill switch, because it's required in the rules. In case something happens to the robot, if it burns out, we can like shut it down before anything happens or hurt anyone in the competition. So, all right. So we're going to get started. So keep these tasks in mind, because I'm going to be asking you guys what you guys want to do at the end of this workshop, so I have a better idea of how many are involved. All right. So the review questions are these. So first question is, what are the components of servo motors? You guys can guess, put it in the chat.
Servo arm.
In terms of
Is that what you mean by?
not mechanical components. That's a good response.
Oh, I'm a mechanical guy,
Electrical
so.
components.
Positive, negative, and there's a third. Oh, signal. Positive, negative, or positive ground signal. Sorry, I don't understand.
That's okay. Magnets. Yeah, there's technically magnets. That's like too narrow. I'm talking about like the general little parts. So I'll give you guys a first hint, is a DC motor. There's a DC motor in there. Yeah, there's copper in there too. More specifically is brushless. And the second part in the servo motor is a control circuit.
Hey, time out. Isn't a servo motor technically like a DC motor, but with like a gearbox, basically?
Can you say it again?
Isn't a servo motor technically a DC motor with a gearbox?
A remote?
Sorry, technically a DC motor, but with like a gearbox.
With a gearbox and a potentiometer and control circuit.
Oh yeah, that's right. That's right.
I kind of gave it away, but yeah, Tim, you got it. Potentiometer. And 4th is a gearbox. And I'll explain to you why they're all combined together in the first place. And then, nice. Battery is actually not included in the servo motor. It's, we use it externally. But yeah, so DC motor, and the reason we use brushless motor is because they can spin pretty fast. And we attach it to a gearbox to increase the torque level. And the reason we have control circuit and potentiometer is to get feedback on how fast and what directions we want the motor to be spinning, okay? So if you think about it, our robot is actually set up as a servo motor, but people have a misconception of where servo motor is essentially the little tiny little things, little motor with little servo heads. Yeah, they are called technically servo motors, but the definition of a servo motor is like a combination of these 4 things. So our robot is technically using a servo motor, but people don't say that because it gets confusing. So let's just stick with like how we usually say it, which is we use brushed DC motor on a robot. Anyway, cool. I kind of gave it away the second question. The second question is, what kind of motors are we using? Yes, it's brushed DC motors. And the reason we use brushed DC motor is because it's inexpensive and it has high torque at low speed, which is what we want. We don't necessarily need our robot to be going really, really fast. So this is why we use brushed DC motors. There's also a brushless DC motors. Most of them are used in like fans and drones because they spin really fast. All right, that's a great question. What is a DC motor? DC motor, basically DC stands for direct current. Okay, meaning that they either turn on or they turn off. It's like 1 and 0, voltage 1 and 0. Okay, and in the internal, I don't want to go into it too much because the video went too more into details. But basically, brushless has magnets on the outside, whereas brushed DC has a magnet on the inside. That's the key difference. But the thing with brushed is that there is the way we kind of supply. This is brushed. Brushed and brushless. The way we would supply voltage into the brush is where we have a little a copper brushes here. It's kind of like magnetizing the magnet in here, and then it allows it to rotate. Okay. And however, the downside of using brush motors is that they can wear out because basically you can cause the voltage is kind of touching this rod here. So over time, because of friction, it's going to wear out. The brush is going to wear out. But for our purposes, it's okay because we're not like using it for a long duration or like for long uses and stuff. So that's okay. However, the advantages of brushless is that it spins really fast and doesn't have this issue of wearing out too much. This is just a little brief summary of what a DC motor is. What is the difference between brushed and brushless with the gearbox? That's a great question. So brushed itself already provides a really good torque at low speed. However, with brushless motors, you can actually just touch the shaft of the brushless motors and it will stop very easily. It doesn't has good enough torque. So what normally people would do is they attach a gearbox to the brushless motors to add a torque, which is how the servo motor is doing. Basically, they use a brushed DC motors, pair it up with a gearbox to increase torque, to basically get the properties of what a brushed DC motor would have. All right, hopefully that answered your question. Okay, sounds good. And lastly, the third question, what kind of motor driver are we using? Okay, this is pure silence, and that's okay. So servo is a components. Servo has many parts. It has 4 parts. Servo motors has 4 parts. Motor driver is the control circuit. It is not L298. I wish so too. Yeah, but it's unfortunately not. Essentially, a motor driver is essentially a control circuit inside of a servo motor. It's not a piece hawk. The black circuit board thingy. You're on the spot. You're on the dot. UW. So basically, our motor driver that we're using is called Cytron. Cytron MD30C. Okay. The reason we use this motor driver is because it can allow it to draw high current. Can servo be made continuous? Yes, actually, that's a great question. So there's a lot of different types of servos motors. In fact, you can actually, if it's not continuous, you can go into your gearbox and like pitch off a thing that's preventing it from being continuous. However, you don't want to do that because once you kind of chip that gearbox little part in the gearbox, it can never be, it will always be continuous and you can never get how you originally intend to have it as. So yes, servos can be made continuous. But that's, okay. So what kind of motor drive do we have? We use Cytron MG30C because it can draw high current, which is what, if you look into the DC motor that we have, it draws really high current up to like probably 60 amps, but like the range that we want to be in right now is 18, which is more than enough. Okay, so before I get into sensors, does anyone have any questions about the first video? Those 3 questions should have covered the important parts of the first lecture or the first workshop. If no questions, I'm gonna go straight into our sensors. All right, I'm just gonna stop right there. Okay, awesome. So sensors, we have a couple of them. I'm going to introduce them, the ones that we use on a robot, which is camera, IMU, LiDAR, encoder, and GPS. And they all play an important role, okay? So let's start off with the camera first. So the camera that we're using is Logitech C920. They're a pretty expensive camera, but they have a lot of benefits. The first thing I want to go over is the USB port. There's actually different types of USB port. Okay, I want to go over this. This is actually very important. So if you see a USB port with the white colored plastic inside, that is USB 1.0. Okay. Now, if you have a USB with a is there a color change here? All right. Yeah, I'm gonna go. This is supposed to be black, so I'm gonna leave it black actually. There is a difference, and I'm going to go over the difference right now. This is USB 2.0. This is supposed to be black. And this is going to be blue. And then one last one is here. It is red. And I'm going to explain to you why this is really important to us in a minute. This is called USB 3.0. There's also a USB 3.1, same color too. And there's USB active. All right, so they all draw different level of current. The more current you draw, that means the more messages you can actually get across the USB port. Okay, that's really important. So for the data transfer for the USB white is 12 megabytes per second. Over here is gonna be 480 megabytes, I think megabytes, sorry, not megabytes, megabytes per second. And this one here, sometimes it can really go up to 5 gigabyte or 10 gigabyte per second. So if you, this is where you're going to see price changes whenever you buy a USB. Really, um, if you see an expensive USB, most likely it's going to be in the USB 3.0. If you see like a cheap USB, it's going to be this. So if you guys, I don't know if you guys have noticed, but like a really ordinary Apple charger has a white USB port, a little thing like this, and hence the reason why they charge very, very slow. But USB-C is different. It allows you to draw more current. Hence the reason why they are actually able to allows you to charge faster. But the downside of letting a lot of current through your phone is that it will heat up, especially if it doesn't have a thermal good thermal I guess cooling down system. A lot of Android cheap parts try to use USB-C, but they don't always account for the heating that the electrical components go through. Yeah, that's just some of the sacrifices they make. So in this case is the data transfer. Yeah, so you can actually, okay, yeah, but they also vary in other stuff too. For example, these two parts, they have a communication protocol of a half duplex. Now you may be asking, what does that mean? Well, what it means is that the connection, what is this? Can someone get rid of this? Okay, half duplex means like you're sending direction, you're sending information, sending messages or info, one direction at a time. Meaning it cannot do, if it wants to send one information, it needs to go to this direction, but if you, let's just say the computer wants to send it to a phone, it needs to wait for this protocol to finish before it can send back. It cannot do simultaneously. Okay, these USBs cannot do that. However, USB has a full duplex here. Okay. Okay, so this means you can send data simultaneously. That's the added benefit of the USB 3.0. They also have different current level. Now you may be asking, why is it important to be going over this? Because it may be not so much important right now in the moment, but in the future, when you want to like get rid of lag in your data receiving part of the robot, I guess, like this is where it comes down to. You may think that it's the code issue, but most likely it could also be just like a simple USB issue that you simply need to fix. Okay, so I'm just going over this to make sure that we also account for this in the future. Okay, so this one, all of these have 5 volts, 5 volts, 5 volts, 5 volts. I haven't gone over the USB active, and there's a reason. If you guys can take a look at your USB, whatever USB you have, you can probably identify what it is right now just by looking at this. And this draws about 0.5 current. 0.5 current, and then 3.1 USB 3.1 actually it's 0.5 amps. 3 amps. The USB 3.1 actually draws about 0.9 amps. It increased. USB-C actually draws up to 1. Where do you commonly see USB active? Actually, I have one right now. I don't know if you guys noticed, but like the USBs that you see normally in your like, actually I'm pretty sure you have this part of this SanDisk, like an ordinary USB disk that you have everywhere, that you use for like putting your files and stuff. They're actually red, and the reason they're active USB is because sometimes what you'll notice is that like in old USB, when you plug it in, they don't recognize a USB sometimes, right? The computer is like, where is it? I don't see it, you know, what's going on? And like, and you always have to like kind of tweak the port just to have your laptop recognize it, and that's and the way to kind of account for that little issues that we used to have in the past is by using the USB active. And the reason we have USB active is because basically it doesn't wait for the host to recognize it. It just sends information directly, and because it doesn't care if the host is either seeing it or not, it just sends it. So whether or not, it doesn't have to go through a gateway in the or whatever the thing is in the on the laptop that's not is preventing it from recognizing it. It kind of goes through that firewall, I guess. I don't know if that's the right word, but yeah. So because of that, it makes USB active makes sure that it doesn't fail. It doesn't fail to have it as unrecognized, if you will. But yeah, doesn't care about the host approval. Cool. Awesome. So that's simply about USBs. This is a lot about USBs and how does it relate to camera? That's a great question. It kind of sort of does and doesn't. The USB that we have for Logitech, I believe it uses a black. It sends a pretty slow data, so but that's okay. We don't need it to be a high data transfer rate anyway. And then the pixel that the camera uses 1080p. So basically what we have is 192 pixel here and 1080 here, pixel here, okay? Basically little squares. Awesome. It auto focuses, which could be a really key when it comes to having like a bad quality image whenever we have the robot in action. And not just that, it also has speakers. Oh, sorry, not speakers. It has microphones, so it's able to detect sounds. I don't know if we're ever going to need that on a robot, but it's nice to have an additional feature. It also has, this is the main reason why we bought this camera, is the low automatic low light correction. Basically, if there's a sun glare, it kind of like corrects the image before it gets sent down to the TX2 to kind of having us use a filter to to basically make a better image for us to use. So that's the feature why, that's the main reason why we picked this camera. And it's also compatible with Ubuntu, which is what we're using. Okay, so does anyone have any questions about this before I move on to IMU? IMU is really fun. It definitely helps with computer vision. Basically, computer vision algorithm just kind of like accepts the data from the camera, and then the CS team kind of like figure out what to do with each pixel and identify the objects they're seeing. Does the autofocus help with vibration? No, it does not. And unfortunately, no. It does not. It just makes sure it's like it zooms and zoom in and zoom out. That's all it does. It doesn't account for vibrations too much. No. That's stabilization, which is something that the mechanical team has to work on. So unfortunately, I'm sorry if we don't. I mean, unless we use a GoPro, which is really expensive. But yeah, cool. And yeah, just use a gimbal. All right, that works too. Why you refer to robot? What should one look like? The robot is okay. I guess I can draw a robot very quickly. The robot that we're gonna be using is like, this is crappy as drawing. Has 4 wheels, and there's gonna be a mass, and there's gonna be a camera, kind of looking at any obstacle that we see. I just say this is RN. If it sees it, you're like, nope, he's in the way. I'm gonna get away from him. So it goes away. So the robot will go away and turn around. So the camera is where that's when the camera comes in handy. It kind of look at what's up ahead to see what's going on. Yeah. So that's when the camera comes in. Cool. All right. Awesome. Okay. Okay. Okay, IMU. IMU has a okay, so IMU has a lot of at least the one that we picked has a lot of features. So it has accelerometer, a gyroscope, and a magnetometer. So here, here, yeah, that was terrible. That's okay. You guys can still see it. Okay, accelerometer basically measures planar acceleration. Let me tell you what that means. So we have three. X, Y, Z. So it measures acceleration from front to back like this, up and down, and Y direction. And it measures all of this simultaneously. It doesn't just like look at one direction at a time. So keep that in mind. That's the, and why does this come in handy? It will help us figure out how fast our robot is going. Okay. So, and now what's a gyroscope? Okay. A gyroscope is rotations, okay? That's the, oops, that's the positive direction. This is the positive direction. And this is the positive direction. All right, so this, we don't necessarily need gyroscope way too much in our case. I mean, except the z-axis, we do. That will allow us to see if a robot is kind of going left and right. But in the x and y axis, we don't really need that because our robot is not going to roll over or anything. Unlike some this is where it comes to an area where it will become useful is going to be like where like Baja car, essentially. There sometimes the chassis might tilt side to side, so they can look into that data and see how to prevent that from happening. And lastly, we have a magnetometer. Magnetometer essentially tells you if the robot is going north, is facing the direction of north, east, west, or south, essentially, and that will help us figure out the orientation of the robot. Okay, so we have all that feedback to allow the CS team to figure out how to help the robot navigate itself blindly, right? So, but let's look at some of these data that I'm looking at. Would an IMU be useful to get a positional data from a robot manipulator arm? That's a great question. An arm. Yes, it will help you, but I will still suggest using an encoder in those joints that you have to further help you figure out the exact location of how the robot is maneuvering. So I will go over that another type of sensor that we will be using, which is an encoder at the very, very last. So yeah, so yeah, to answer your question, yes, it would help. Is this related to computer science? Sort of, yeah. I mean, all of the data that we basically collecting from all of our sensors is going to the CS team for them to manipulate and tell the robot what to do. So yes, it is related. But yeah, the EE team is figuring out how to hook everything up, making sure that there's no noise of any kind from these sensors when it's shipped off to the CS team. But again, like there's always going to be noise, so the CS team will most likely going to have to put another filter on their on those data to sort it out even furthermore to get really quality data. But yeah, okay. So let's look at what these couple of these values means because they're really important. Okay. So when it says range, I'm going to erase some of this because I want to make sure that I have these notes. Actually, no, I'll go down actually. So range here, plus or minus 4g. G basically means the gravitational acceleration, which is 9.81 meters per second squared. And 4g, so why does this matter? The amount of let me make that sure. Okay, so if you want to measure like tilting wise, you only need to have like what the threshold you need here is like 1.5 G, 5G for tilting. If what you worry about only is about tilting stuff in your project, I suggest you buy a cheaper IMU with the threshold of 1.5 G. Okay. Now, let's just say we need how about 2.0 G? 2.0 G is enough to figure out the motion of a car, you know, or a plane, or simply like a set or a robot. Okay, this is where this threshold is acceptable, and that's okay. It still gives you enough data, good data. Now, lastly, there are some cases where you have plus or 5G. Okay, this is where you're going to want to measure the impact of certain things. Yeah, so let's just say this is most likely going to be used in like brakes, because you need to have a really because they go through some basically it measures impact impact data is mainly used for impact stuff. So I don't know if you guys remember from Strengths Lab, if you haven't taken it, there will be a pendulum. There's a part right here, and this pendulum will go into here. And if we have this IMU sensor that can like kind of see what's happening. So what's going to do if it's 5G is that it's going to measure every single little detail of what's happening when the pendulum strikes the material. Okay, so this is why it will be very useful to get a really expensive IMU, because they can give you really good data. Okay, but we have a the IMU we have is plus or minus 4G, which is really good and enough already. So I wouldn't worry about it too much. And it wasn't that expensive either. So yeah, props to whoever built this thing. Anyway, now to go over the range, bandwidth. Bandwidth is really important, you guys. It's, okay, let's see, how do I, okay. Slow moving tilt sensor, vibration analysis. Okay, so basically bandwidth measures how fast you want, or how much data and how fast you want your data to be transferring to your user or the receiver, the update rate. There you go. So basically, this is it's hertz, and hertz is cycle per second. So let's just say this is time. This is 1 second. It's trying to see how many cycles it goes through in 1 second. So the higher, the better. Okay, it gives you a better update rate. The faster, so you will want a higher bandwidth if you want a really accurate data, so that the IMU can look at where it is at. Where is that in a faster, like let's just say it can see every, like it can give you like more data in 1 millisecond kind of thing. You know, you want a faster update so that the robot can make faster decisions, if you will. Okay. Okay, bandwidth. Okay, those are necessarily all the important features that you guys need to know when picking out an IMU, essentially. So, any questions before I move on to LiDAR? Okay, I guess not. LiDAR. LiDAR is really fun and is dangerous to your eyes too. Okay, so it accepts 5 voltage. So it uses 5 voltage. And the LiDAR that we use takes about more than not less than It's actually more than, it accepts more than 2,000 samples per ray. So right here. So what we want is this particular, so right now we're at default setting, which is actually doing this right now, by the way, our LiDAR can go up to here. So if you want like more possible points or more data from LiDAR, we have to go into the settings to change that up for the future. So most of LiDAR, how does it work? Well, LiDAR essentially spits out little lasers. So let's just say here, it's actually described here very perfectly, but I'm gonna draw it here again to kind of, yes, you have enough errors now, okay. So let's just see a wall. It sends out data and it reflects back. Okay. So what's interesting about, okay, but when I was learning about LiDAR, I always wonder, why does it bounce back? It doesn't make any sense, you know? Like you don't see it bouncing back. I mean, you may see it reflecting you may see it reflecting back of mirrors, but like you may be asking, how does it know like how to, you know, bounce back in a particular direction and stuff? So which that actually comes in the type of laser you're using. So so the laser, I guess, frequency that we're using, it is, where did it go? I just had this down. It is a low power, less than 5 milliwatt laser. And so but the thing is that it's not like turned on the entire time. It goes off in a modulated pulse. So it's like blink, 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 you know? And it's a good thing that you have it like this, because if you directly stare at this laser for like even like 1 minute, you can go blind. So or like you can have like itchy eyes and stuff already. So it's dangerous to stay in front of this laser 52 feet away, which is this is a dangerous range. So if you're even closer to it, to the laser, that means you're really at a situation where you can lose your eyesight. So the safe distance is about 2.2 miles to be away from this laser, which is really far. That's how far they can travel. What is the frequency of this? I actually do not know. I'll get back to you on that. If you're still interested. Can a LiDAR detect transparent objects? It kind of. What do you mean transparent? Like a see-through acrylic? Yeah, I'm not too sure actually. It depends on, but it does reflect off mirrors. So if it has enough reflection as what a mirror would have, it would be enough to reflect back. But the reason it reflects back is because of this particular laser. It's because it has what they call it a vegetation. Okay, basically green laser and red laser can reflect back off the radar. Yeah, as a LiDAR, so it's basically a radar in a way. Basically, if it sees some sort of vegetation of an object they're seeing, it reflects back. Okay, but any other types of, not red laser, sorry, green and near infrared. These are the two commonly used lasers that we use on devices because they allows the whatever objects that we have to reflect back. Hence the reason why LiDAR works the way they do. Okay. Is the danger only if the eye are in the same Z plane as the LiDAR? Z and X and Z. Basically, if it's looking directly at you, bro. So how do you say it? Sees your eye. If it points directly at you, then you're screwed. For a long time, not for a short time. Short time is fine. Yeah, if you're above it, you're good. Yeah. But just don't let it shoot at your eye is all I'm saying. Are we using this for gauging distance? Yeah, so the data it gives off is this. It gives you two types of data. Okay, so let's just say you have a LiDAR here, and this is an object. It gives you this distance, and they do have a reference angle, and they give you this data, this angle. So it gives you the distance it travels, and it gives you the angle. That's the two data that this sensor gives you. Wait, are we using this for gauging distance or object detection or both? Object detection and gauging this isn't the same thing, bro. If you think about it, Stu. Ultrasonic sensor. Oh, that's a very great question. Main pros. I believe LiDAR can travel more, but ultrasonic sensors, I believe. Actually, I haven't worked too much with ultrasonic sensor. I'm sorry if I. Okay, I think I can answer that question. Full range around the robot with LiDAR and ultrasonic one direction. Are you sure? That doesn't sound too. Okay, but I can. I'll look into it and I'll get back to you. But I'm gonna move on for now. Okay. So before we move on, does anyone have any more questions about the LiDAR? Because I'm gonna be talking about the encoder afterwards. Yeah, that's a good point. But some of the LiDARs only have, most of the LiDARs that's like really good quality can only go up to like 270 degrees though. Not all LiDARs have the ability to 360. And again, LiDARs are mostly used for a longer distance. For example, they're actually put on airplanes to actually figure out the altitude of land and stuff. And yeah, so they don't use ultrasonic sensor for that. They use LiDARs. And like I said, the reason, another big pros of LiDAR is that it can detect vegetation. That's a huge part. Meaning like they can, just you have a plane here, you have land, they can actually recognize the trees because leaves are basically the leaves. They have green pigments, so they can actually figure out the details of the structure of how the trees are. I don't know if ultrasonic sensor can do that. They just probably show you a dot, but the LiDAR can show you the little details and the nitty and gritty stuff of a tree. Okay, cool. Okay. Cool. So encoder is actually pretty cool. My favorite one too. So no more question about LiDAR before I move on. This is I have two more, so I'm gonna maybe speed up a bit. Okay. Okay, I'm gonna go to encoder. Encoder is so what I want to focus on is this. Two channel quadrilateral. Yeah, and I want to explain what that means. So let's just say we have a circular surface that's being rotated. It will be rotated because of the shaft. And it has boom, 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 boom. I think. Okay, and let's just say you have a little thing that's kind of sensing if it's white or if it's black or if it's white. Okay. Yeah, I'm aware. Thank you. So as soon as the motor starts rotating, this little disc also rotates. Okay. So if it rotates clockwise or counterclockwise, let's just say clockwise, this is up to how the thing is designed, but like most likely if it's black, it's gonna give you a value of 1. If it goes to the white side, it's gonna give you a value of 0, and so on and so forth, right? 1 0 1 0. But the issue with just having one feedback is that, let's just say you go from this side and this side. You don't know if this motor is turning like counterclockwise or clockwise. It doesn't know that if it just have this one input. So hence why we need two channels. Okay, so if it has two channels, what's going to happen is, let's just say this is A, this is B. Okay. So this is going to go into what? Just say 1, and this is going to be in 0. If it rotates clockwise, it's going to be 0, 0, because both of these sticks will be in the Y zone. And then after that, it's going to be 1, 0, 0, 0. Actually, hold on. I got to draw it better. Let me just make this. This is going to be 1, 1, 1. So if we go clockwise, it'd be 1, 0, 0, 0, and 0, 1. And 1, 1. Okay, so basically what this allows us to do is actually help us figure out the direction. So if it's going this way, or if it's going that way, we'll be able to indicate if it's going clockwise or counterclockwise. Hence the reason why we have these two channels to dictate rather or not if our encoders is, basically help us indicate direction. And this will also help us figure out the ticks. So basically one section is 1 tick, 2 tick, 3 tick. And if we actually have that making a graph with where the Y is going to be the ticks and the X is going to be the seconds, it'll help us figure out the velocity of how fast the robot is moving. Not just velocity, but it'll also help us figure out the displacement of where the robot has been. Because if we have, the data sheet should have this, the data should figure out, tell us how 1 tick is worth, how much rotation would have moved if it was just 1 tick. And from that, we can figure out how much robot has traveled as well. Cool. Okay, all right. Yeah, encoder is pretty easy to understand. Now for the last thing, GPS. So GPS is actually pretty fun too. GPS actually it's pretty new technology. It was, when I looked at it, it was 1995. I thought it was way much older, but no, it was pretty recent. Basically, there's 3 components to GPS. There's satellites, ground stations, and receivers. Ground station kind of accounts for to see where the satellites are at and making sure that they're always in position. Receivers are us trying to figure out just to see where we're at. Just to get feedback. Our robot still uses a paper map because it's built different. Okay. Yikes, I'm worried about that if we're doing that. Okay, so there's actually a total of, well, they claim that, and I don't believe this too much. There's a total of 32 satellites made for GPS, and 22 of them, we use them daily, and 8 of them is used for emergency. Okay, and the sensor that we have, the Otterfruit GPS breakout, it's, well, to get an accurate location, people say 3 or 4, but it's actually 4. You only need 4 and feedback from 4 satellites. So this is how it works. So let's just say a person tells you, let's just say let's just say I got hungover and then got into some other place I don't know, Kansas, but I don't know what Kansas, I don't know where I was. Let's just say I don't know. I asked a stranger and I see R and he said, you're about 10 miles away from this city, right? So that gives me that gives you a location of some sort. And I asked another person, and this person said, you're particularly away from this location. Gives you another location. So you have 2 intersections here, right? And those intersections tells you where you're at. right? And if you have a feedback of another person and another person, you're basically likely to figure out exactly where you're at. But so hence the reason why you have 4 satellites to really determine where you're at. The beauty about satellites, like it's not only does it like um, now it doesn't not only does it locate where you're at. The fourth satellite also helps you locate your altitude. Basically, if you're like below ground, above ground, and stuff like that, or in the air, that's what the fourth satellite is for. If you guys don't know, I didn't know until like last year. But that was pretty cool. And these satellites are meant to be last for about 10 years. So every 10 years, they need to ship a new one out there in space and then use that one. So hence the reason why there's a lot of CubeSat going on. And let's see, you need 4 channels enough. Basically, one channel for one satellite. But the reason why there's 32 satellites to begin with is because, for example, right here, you have 22 tracking and 66 searching. There's a lot of channels because I don't know if you guys ever scroll through like your TV. What's happening is that sometimes, or the radio actually, sometimes you hear a little bit of the music, but if you switch it to one little different channel, you get a better feedback. So that's basically what it's doing. So hence why like our GPS is actually searching for 66 channels simultaneously to give you a feedback that's pretty good for us to work with. But even with that, sometimes we get crappy data, and I'm pretty sure Ari can say that. But but yeah, and it looks for 4 satellites, and it's always looking at 4 channels to figure out where we're at. Yeah, I don't know if that makes any sense to you guys. Any questions? I kind of went over the last few slides pretty quick because of the time. 10:57. I have 3 minutes. Okay, any questions, guys, about all the sensors that we have on our robot? Hopefully this gives you a better idea of why we have these on our robot to help the robot visualize where we're at. Okay, cool. So, if you guys don't have any questions, or I'll give you guys time to think about it while I want to go over something else. So yeah, now that you know what these sensors do, I want to go back to the task. So like I said, for those who kind of came in late, there's 3 tasks for the ASME team. One is making a remote controller. So remote controller task is going to be pretty important for other challenges. So I know the IGVC has to be autonomous, but that's not the only challenge that the IGVC competition has. There's like 2 or 3 additional ones, but those are like now required to do. But it's nice to have them work on it. Basically, a remote controller is going to need to have a lot of data, such as like the speed is going. What else? Actually, the other one. There's more stuff you can give, obviously. But I'm saying that the remote controller allows us to test run the robot before we even have the CS people have it done. Basically, remote controller is mainly towards for the ME team to figure out the suspension, all that stuff to see how they might work out. So remote control is really important. Power distribution is the task that needs to get done before the remote controller. And 3 is the emergency electrical mechanical fill switch. That needs to get done probably like very last thing, but it's better to get it done ahead of time. But yeah, so with that said, if you guys have any interest in any of these tasks, please email us. So, oh, that's a great question. I'm glad you asked. Okay. Where to go? Yeah, so it's forced. So that means that magnetometer is actually not turned on um, automatically. Like you gotta like change it in your settings to kind of turn it on. Um, so basically, it's not like so you have to mess with your default settings. It's like basically you have a new like a like a let's just say a switch, right? You have to go to your settings to change your perspective and stuff and to turn on some of the features. So yeah, IMU has a lot of features. Aaron, and you should take a look at it too. It has more than what it can offer that we think, but and it can actually also provide more better data if we mess with the settings of the IMU. There's actually a software out there that allows us to actually get in touch with the IMU settings. So, but yeah, that's what the force means. It's not turned on like right away. You have to kind of like go into your settings and turn it on yourself to use that data. But yeah. Um, any questions? Good question though. Oh, okay, so one last question. I know I just went over the time, but do you guys prefer me writing it out like this or just like having a presentation and just verbally kind of going through it? Because I know in the first workshop, that's what I've done. In this workshop, I did it differently. So which method do you guys prefer? Me going like writing it out or okay, cool. All right, awesome. Yeah, I'll write it out. Okay, sounds good. I'm gonna stop sharing and so Sindel, do I stop the recording or pause it?
I would stop it and then just we're gonna start recording again once Arn is ready.
Oh, okay, sounds good. I'm gonna stop the recording if no one has any more questions. 5, 4, 3, 2, 1. All right.